Welcome to the New Quantum Era. I'm your host, Sebastian Hassinger. One of the threads I keep returning to on this show, whether I'm talking to hardware builders, algorithm theorists, or application researchers, is the question of honest accounting. What has actually been demonstrated? What is genuinely projected based on sound reasoning? And what has quietly drifted from scientific hypothesis into received wisdom without anyone quite noticing? We've had some fantastic conversations that live in that space. John Preskill, back in episode 15, was careful and precise about the long road between near-term devices and fault-tolerant computation. More recently, Dominik Hangleiter, in episode 86, unpacked what it really means to claim quantum advantage and how hard it is to prove it rigorously. And in episodes 30 and 31, Lin Lin and Jamie Garcia both wrestled from different directions with what quantum computers can realistically do for chemistry in the near term. Those conversations all circled the same honest question. Where exactly is the line between classical and quantum capabilities, and how confident are we that we know where that is? Today's guest has probably done more than anyone in the world to actually locate that line, not by arguing about it, by actually moving it. Before we get into it, this episode is brought to you again by Qubits OK. If you're building a career in quantum or hiring for one, Qubits OK is the signal in the noise. It's a dedicated job board and research digest for the quantum computing community. Every week, curated job alerts filtered by over 400 specialized quantum tags. So you're seeing roles in trapped ions, QEC, quantum ML, and whatever else actually matches your work, not a generic tech spam. They also run a daily archive digest that surfaces the papers relevant to your specific research interests. Around 100 archive authors already subscribe to that feed, which tells you something about who's finding it useful. It's free to subscribe. Just head to qubitsok.com and sign up. It takes about 30 seconds. And if you're on the hiring side, use the code NewQuantumEra-50 for 50% off your first job posting. That's qubitsok.com. Code NewQuantumEra-50. Now, Garnet Chan. Garnet is the Bren Professor of Chemistry at Caltech, a member of the National Academy of Sciences, and one of the most cited computational chemists in the world. His research sits at the intersection of theoretical chemistry, condensed matter physics, and quantum information, developing the numerical methods needed to simulate quantum many-body systems, and asking, with genuine rigor, what makes these simulations hard. What makes his perspective so clarifying is that he is not a quantum computing skeptic in the dismissive sense. He uses quantum information concepts in his work. He's written careful, balanced reviews of quantum algorithms for chemistry. When I first met Garnet years ago, he said he would use a quantum computer tomorrow if he could do something on it that he couldn't do with the classical computer. The operative word is could. And for over a decade, he's been the researcher most willing to put serious effort into finding out whether we actually know the answer. That work recently produced a result that sent ripples through the quantum chemistry community. Without getting too far ahead of the conversation, there is a molecule, a biological catalyst at the heart of one of the most important chemical reactions on Earth, that has served for years as one of the canonical examples of a quantum advantage use case. It has appeared in resource estimation papers, funding arguments, congressional testimony. Garnet's group took a hard look at the specific computational model that had been targeted. What they found and what the result actually means and doesn't mean is something I want you to hear directly from him. Because Garnet is careful about distinctions that often get lost in the discourse between a model and a mechanism, between a benchmark and a proof, between classical hardness as a presumption and classical hardness as a demonstrated fact. He felt strongly enough about those distinctions he did something he'd never done before. He wrote a public piece explaining his own results because the misreadings were arriving faster than the conversations could correct them. He came to theoretical chemistry from Cambridge, where he'd started in the experimental lab before realizing that the wet bench wasn't for him. The appeal of theory, he said, is that your computer does the same thing every day, a deeply relatable sentiment for anyone who's fought with finicky equipment. But what you'll find in this conversation is a theorist who is drawn to the hardest, most resistant problems precisely because they give him room to keep running. This one is genuinely thought-provoking, regardless of where you stand in quantum advantage. Let's get into it. Welcome, Garnet. Thank you very much for joining me. I know a little bit about your background. I think it's really interesting. Can you start by sort of describing a bit about what your path has been to where you are now as a
Sure,
professor
sure. I mean,
at Caltech?
well, I've lived around the world, but I think from you know, a science perspective, um, I studied chemistry as an undergraduate in the UK, Cambridge, and chemistry is mainly an experimental science. Um, but despite my, dreams of synthesizing complex organic molecules, I soon discovered it just wasn't meant to be. Um, but fortunately, I had a backup where after taking quantum mechanics, I felt like, at least you could, think about making molecules by following just the laws of quantum mechanics. So that's how I transitioned to a theoretical chemist. And that's what set me on the path, to where I am today.
You've mentioned you prefer theory in part because your computer is
Oh, yes, yes.
dependably doing the same thing every day,
Yeah.
as opposed to sort of the wet
No,
lab
no,
and
I
all
say
the
this
intransigence
to
of
students when
the
I'm trying
wet
to
lab
convince them.
going.
It's like, do you really want to wonder whether tomorrow's experiment's the same as today's experiment, or do you want to know that you get the same result every time? And that's of course the joy of computing.
It's really interesting to me, that chemistry is in many ways one of the catalysts that actually brought about the field of quantum mechanics. Right? It was sort of trying to answer questions from the field of chemistry that were puzzling
Yes.
the scientists of the day. Do you think? I mean, do you think that? In terms of chemistry, do you think your starting point is quantum mechanics, or do you think sort of at the chemical formula level and then dig down to the quantum level when you need to,
I mean,
or does that
it's
does that
it's sort of
distinction make
interesting.
any
So
sense?
people, quantum mechanics originally entered chemistry in the theory of bonding, into the theory of atomic orbitals and molecular spectra, and what makes molecules stable, chemical bonds, and so on. The interesting thing about chemistry is even before the quantum mechanics was discovered, there were sort of rules for how things bond, and you still learn them in high school. There's like electron pairs, and you count. There's a rule of eight. So there are all these things, um, but it was a kind of meta theory built to rationalize experiments. Um, and the foundation of it all came later after quantum mechanics was first discovered. Um, but nowadays, I think the way that people usually think in chemistry about bonding is they talk about some entities which only appeared after quantum mechanics appeared, like the idea that they're orbitals and electrons are delocalized and so on. But nonetheless, as an experimental chemist, they've once again built this meta theory on top of it, where without any mathematics and any calculation, they have this feeling about these orbitals overlap and they make a bond. This one has good overlap. There's orbitals pointing in that direction and so on. So they built some kind of empirical understanding, on top of these sort of quantum mechanical entities.
That's really interesting. And I mean, in some sense, it seems like you were drawn to really resistant theoretical problems, and trying to find solutions. Is that in part sort of trying to find new ways to apply those quantum mechanical principles to the challenge of a particular theoretical problem, or trying to discover new aspects of the
Yeah,
behaviors, the underlying behaviors, or
yeah. So
how do you? I mean, how do you think of that?
I like to say that I don't want to work on too many chemical phenomena. So there's sort of different modes of being a theorist, and um, you know, a lot of the time, what we actually do in our research is like work on new algorithms or basically theoretical things that don't immediately, aren't immediately applied to create an output that a chemist cares about. Um, and so consequently for us, it's sort of in this mode where we're doing a lot of what we call methods work and algorithm work. It's nice to have a small number of targets, and since you don't want those targets just to be solved easily by someone else, so you have to pick a different target. You basically wanted to pick some very difficult target so that you can kind of stay on course for a long time. And so that kind of so the philosophy why I like to pick these problems that give me a lot of room to run while I'm thinking more about how to solve quantum mechanical equations.
Interesting. So the trigger for me reaching out to see if you had time to come on the podcast was a recent paper that your group released in January. It was called "Classical Solution of the FeMo-cofactor Model to Chemical Accuracy and Its Implications," and then an even more recent blog post where you sort of provided some meta commentary on the paper itself. Let's start with the paper. FeMo-co is of particular interest to the field of quantum computing in many ways. Can you explain what the FeMo-cofactor, however we pronounce it, is it FeMo or FeMo cofactor,
FeMo-cofactor
actually is, and why it's important?
Yeah. So,
thank you.
Well, the cofactor is part of an enzyme, the nitrogenase enzyme, and nitrogenase is part of the nitrogen cycle of the planet in the sense that there's nitrogen in the air. It gets incorporated into biological organisms by first being converted into ammonia. And this bacteria is the one that's responsible for converting, doing most of the job of converting nitrogen into ammonia. And enzymes are usually usually have different pieces to them. And there's sort of the piece where usually some chemistry is done, that's the reaction site. And in the case of nitrogenase, that reaction site is the FeMo-cofactor. So it's this central piece of the enzyme. And it's distinguished from the rest of the enzyme by having metal atoms in there because most of biology is sort of carbon, hydrogen, oxygen, nitrogen. And they don't necessarily do that interesting chemistry, but metals are capable of catalyzing reactions. And so biology often uses metals to catalyze difficult transformations. And the FeMo-cofactor has a lot of these metals, what we call transition metals, in its structure.
And that transition or the conversion of nitrogen in the atmosphere to ammonia in soil is basically how all plants get the majority of their nutrition.
Exactly,
right? I mean,
right.
That's fertilizer. Essentially,
so proteins and DNA both have nitrogen in them. This basically comes from the air via this process where it gets into the roots of plants via these bacteria converting into ammonia. And ultimately goes to animals and all living things.
Right. Yeah. So it's truly a fundamental building block of the circle of life, and yet and it's omnipresent. It's everywhere around us all the time, and yet it's very, very difficult to understand on a theoretical basis. Right. The model for what's happening within that catalytic process is
it's still very mysterious. We know the inputs and we know the outputs, and with actually a heroic effort, we know the structure of the enzyme. This was actually took 30 years, but we know the structure of the enzyme. But there's a sequence of steps by which one molecule is converted into the other. Some atoms are added, some atoms are subtracted, things move around, and that sequence of steps, which we call the mechanism, it occurs on the atomic scale. It's very hard to interrogate experimentally. And as it turns out, it's very hard to also, study computationally. So we don't understand the mechanism.
Right. And I think my sense is that FeMo-co has been latched onto by the quantum computing crowd in part because it is computationally challenging, but also because it's a potential use case for quantum computing based simulation that could have real world impact, because the way that we make fertilizer as an industrial process is Haber-Bosch, which is a very, very wasteful compared to the bacteriological nitrogenase process, very wasteful, very high temperature, lots of waste product, and uses something like 1.5% to 2% of the energy input output of the whole planet to create fertilizer. So I think there's a sort of imaginary leap of like, if we could simulate this process, we might be able to improve upon the Haber-Bosch process and make artificial fertilizer in a much less polluting and less energy intensive way.
I think this is the way it's framed.
Sort of the way it's framed.
I do want to say I don't think the framing is is very accurate because actually bacteria consume more energy than the Haber-Bosch process to produce ammonia. So even though in the industrial process people put a lot of, they make the conditions look very extreme. So it's a very high temperature and very high pressure. That's in part because they want the reaction to occur very quickly and very rapidly. The bacteria do it at a very slow pace, but they use uh, at least the same amount, if not more, energy to break the nitrogen bond. Because it's a sort of thermodynamic thing. The bond is very strong, so to break it, you just need a lot of energy. So it's quite. I think it's difficult to claim that if you just replaced the Haber-Bosch process by nitrogenase, you'd save any energy. But it's possible that you can. The bacteria have their own inefficiencies, and so there is the possibility that you could engineer the bacteria to. One of the sources of the inefficiencies is where they get their electrons from. And there's the possibility, for example, of designing some other process where you feed electrons from somewhere else, and then it goes to this enzyme, and it's just another apparatus which we get to play with in the quest for more efficient nitrogen, fixation or ammonia production. But indeed, it's really commonly sort of stated that in this context that somehow will save all this energy, but it's not really very accurate.
Right. And part of the framing is also, if it's not said explicitly, it's sort of implied that this is in that class of problem that is intractable for classical computation and may only be solvable through quantum computation. That brings us to your paper that your group put out in January, which classically solved the ground energy state of the FeMo-co, right? Of the actual. So tell me a bit about that work. It's theoretical, but you have a full theoretical solution for calculating the ground state.
So if we sort of further abstract the problem, there's understanding nitrogenase to understanding this particular FeMo-cofactor, and then all the way one can just go to let's just compute the ground state energy accurately, which is a very sort of focused piece of this question. That sort of was, I think, defined in the quantum computing community as a good target because it's easy to state. It's like a mathematical problem. There's a Hamiltonian. I want the energy to some fixed error. So it's easy to kind of to understand that whether you're doing well or poorly for that target. And so what we did in this paper was just say, for the same target, the same Hamiltonian and so on, can we compute this energy to the accuracy that people have been targeting classically? And in this kind of task, it either, depending on whether you have any prior information, it either looks impossible. So you say, I want to compute the ground state classically of a Hamiltonian that's defined a space of 150 qubits. That looks like it should be an impossible task, which it is in the most general case. But all chemical and physical systems are highly structured, and so you essentially know a lot about what physical states look like. And in real world systems, and entanglement's very fragile. They're just generally not very entangled. So that's essentially how we can compute it, because essentially the ground state is only a slightly entangled state, and it's a question of finding what kind of slightly entangled state it is, which is a kind of classical search process. So that's what the paper really tries to do.
That's really cool. And so, if I'm not mistaken, you use tensor network, right?
We use some tensor networks
to actually model
and we use also some other types of quantum chemistry method, couple cluster, which is essentially saying, if I give you a not entangled state, can I build in some fluctuations and correct to add in a little bit of the entangled nature. So we combine these two, we cross-check these two methodologies to feel sure about the result.
Interesting. And what's the computational workload that sort of produced the experimental result?
What's the level of resources that we need?
Yeah, I mean, what would you need to actually run this?
So there's different ways of measuring this. So in practice, I think we gave the exact number of hours, but I think you can run it for you're on a small cluster, and you need like a few weeks or something of computation time. So it's to do everything that we did in the paper. But if you had if you sort of had infinite parallel efficiency in a much larger machine, for example, like use a whole DOE supercomputer, then you could run it maybe in a few minutes or something like that. So it depends on that.
Wow. Okay. And it sounds like what you're doing is as you said, it's a highly structured sort of set of interactions or conditions, and so you're using what you can assume about the parts that are well defined or structured in a way to essentially make it into a sparser problem, right? Something that is more tractable to a tensor network, where you can break down the connections between the dynamics between the attributes that do need to be calculated into a smaller subset of what
the whole Hilbert space,
system
but
is.
Really,
Is
just actually
okay?
A very small section of it.
Right. You're ignoring the whole thing because most of it doesn't make any difference to your
and in
end
fact,
result.
most things, are actually not very far from a product state. This is kind of just the life of a chemist or like practical scientist. They're just not very exotic. But even if you say the ground state is encoded in a classical string, it's just a product state, there's still the question of which one it is. So even if I tell the answer is just a classical bit string, you still need to search over all the bit strings. So in practice, a lot of the classical computation kind of is involved in this type of search. And again, it's not an exhaustive search. You need a heuristic because, again, just the number of classical strings is very low.
Right. But I mean, even given those constraints and that it's heuristic and not exhaustive, your result is still, it's accurate to sort of the laboratory standard, right?
It's accurate
sort of
to the
computational
standard that was defined that people use in quantum resource estimation. I mean, experimentalists is maybe looking for different things. I mean, not necessarily. Not. I mean, they may not even care about the ground state energy, but as this problem has been phrased as a target for quantum computing, this is the problem statement. So it's within the same accuracy that is used in the problem statement.
And you mentioned, in natural systems, or entanglement is very fragile. So it doesn't spread or propagate or last a long time. So it's there's sort of a natural narrowing of the problem state, if you will. Do you think that's sort of a generally applicable sort of principle that perhaps diminishes the necessity of having large-scale quantum computing to simulate these systems?
Yeah, I mean, I think it's a reality that I know that to a good approximation, you and I are not entangled. Like we can deduce our properties without thinking about that, and that's essentially how people think about molecules. Atoms are distinct entities. We can define as a local entity, and I'm able to define as a local entity because its properties are not intrinsically completely tied up with some other thing. So I think it's simply just consistent with our observation. And there is various um, you know a lot of quantum computer science is based on rigorous proof, but there's a lot of heuristics or justification for why this is so. So like the interactions between things are quite local, right? We know just the physical interactions are from physical laws are local, and local Hamiltonians. There's a reasonable argument that a lot of them have ground states which don't have a lot of entanglement and so on and so forth. But even though these things aren't completely proven as statements, there's also some mathematical understanding of why it's likely this is true. So I think it's just the case that yes, normal things are not that entangled, but that doesn't rule out quantum computation as having the possibility for some type of advantage in studying these things either. But the thing that I'm always trying to get across to people, ever since people have been talking to me about using quantum computers for chemistry, is actually chemistry is a strange example of a subject where everything in some sense is quantum, but we've been able to understand it with quite simple concepts. So it's a kind of simple subset of quantum, right? It's not like like how Shor's algorithm works, where it just requires some really very quantum thinking, right? And so chemistry is about much more mundane things. But even in this mundane setting, I think there is a role for quantum computers. I think that is also that's also true.
Yeah. I mean, I find your work is really interesting because, this isn't the first sort of, I think, I can't remember if it's Scott Aronson, but somebody has coined the dequantization of, of a problem by coming up with a classical solution that sort of raises the bar in terms of what a quantum computer would have to do to show advantage. But you're always very quick to say that you do think there could be value in quantum computers. You just want there to be more rigor and thoughtfulness and accuracy in how that advantage is defined or explored or measured.
That's how I think it. I mean, the reality is, right? If you gave me a quantum computer, there are new algorithms and new things I can do with to simulate quantum systems, and we will definitely use those new techniques. But I don't think the advantage comes because of this, unfortunately, slightly, often quote statement from Feynman that, well, nature is quantum mechanical, so I simulate with a quantum mechanical system. I mean, I don't think that's really how the world works. I mean, the statement is kind of a tautology, maybe, but
yeah, exactly. Uncharacteristically reductivist for Feynman, actually.
In reality, not everything is super quantum mechanical, right? You should say.
Right. And he wasn't getting into it's taken as a blanket statement. We're not sure exactly that he meant it in that way. But yeah, so I mean, this is a classical calculation of a ground state of a specific model of FeMo-co, not the full enzyme. Do you foresee there being some sort of threshold, maybe in the trying to simulate the dynamics or in the excited states? Is there something in FeMo-co that you think potentially could be beyond classical means and will require?
So again, I think let's distinguish between something being challenging to do and what computer scientists think of as easy and hard, right? So I think that if the question is, do I think there's some setting of relevance to chemistry and biochemistry where if I sort of move from this state to the other, it goes from something that it looks like it's just polynomially hard to solve to something exponentially hard to solve. So I don't think anything like that it happens at all. It would be very strange if it did, in my opinion. But that doesn't mean that the problem is easy to solve classically. So to give a simple example, I mean, what you really would like to do to understand the mechanism is you want to watch the enzyme spit out ammonia, have N2 come in and ammonia come out. And that process takes about 1 second. So 1 second is, of course, short for humans. But on the time scale at which you usually move the atoms, like a time step to move them around, that time step is 10 to the minus 15 seconds. Usually a femtosecond. That's 15 orders of magnitude. Yeah. So bridging those 15, so even using Newton's equations, right, bridging the 50, so assuming zero quantum mechanical effects, like 15 orders of magnitude is not actually conceivable, cannot bridge it directly. Right? Now, it's an open question whether quantum computers, so my first part of my statement is, even though it's polynomial cost, let's say just solving Newton's equations doesn't mean it's easy to do. And then, of course, there's the question of, well, okay, maybe it's not easy to do. Does quantum have anything to to say about this, and that I'm not sure, right? Like will quantum allow us to bridge this timescale? I think it's not clear. It's not clear. So, but yes, it's not so much like, sometimes I've seen some response to what I wrote is simply that, well, if we just made a slightly larger model, then it'd be completely classically intractable. But it's not of that nature. I mean, it's kind of like, even if we made it larger, it would just be slightly harder. That's the nature of the problem.
I see. Yeah, and going back to reactions to the paper, was the reasoning behind the blog post? I mean, you said it's you haven't done this before, offered commentary on a research paper. Was that because the reaction was trying to sort of, in general, was trying to sort of decide whether you were anti quantum computing or skeptical quantum computing, or was it misinterpretation of what the research
I think
thrust
there's
was
some
about?
component of that. I mean, I think, people ascribe all sorts of thoughts to me that I don't know that I've ever thought. But also, I mean, the watching quantum chemistry in the last 10, 15 years, ever since quantum computing has sort of adopted quantum chemistry as one of its areas, has been kind of interesting because, of course, a lot of papers are written. It's an enormously active field. But a lot of those papers are, from my traditional background, I would view them as really just commentary, or, people are just hypothesizing things or making predictions about, what might be interesting. I mean, they're just, a lot of it is really opinion rather than what I traditionally think of, as sort of the science of the field. And I guess I've noticed that, I guess some of my thought was, if everyone is just writing commentary essentially all the time, I mean, at some level, I have a responsibility to provide some commentary on my own work, So otherwise, you leave it just open to misinterpretation, and I try to do that.
Right. This sounds like an iteration of the problem of the internet itself that everybody experiences in some way. It's a medium for opinions and not necessarily constructive work. So I understand that complication, and I guess in a sense, you've said before that you believe that there's potentially the most important thing that quantum technologies have given us so far is just better ability to control quantum systems with precision, and the learning that has come from that. It's almost like the the production of the artifact of a full stack quantum computer is secondary to the understanding and the techniques that we're developing along the way. So those have value into your research as well, even though we're talking about
I think the ability for
engineering
quantum control
systems.
has immense impact, and it will be much broader than just building a quantum computing device. And indeed, the ability to do quantum control is entering into experimental chemistry as well. I mean, I think the real sea change will happen if one day, and this will be, I'm at least confident to say this will be in the distant future. Chemistry is so concerned with a quantity of matter that is relevant at the human scale, which is a lot of matter, 10 to the 23 atoms. And one of the reasons why like quantum effects like kind of get washed out is because we don't control it in any way. So everything is under this extremely poorly controlled dissipative environment. That's why chemistry experiments, you don't need to specify the precise things, quantum state. But if in some distant future we can control a number of atoms that's relevant on the macroscopic scale to quantum control, then the only way we can understand it will be with quantum computers, right? Because but that is at least beyond the I think my academic career, right? That's a challenging, big challenge.
Yeah. Yeah, that's really fascinating. That's really interesting. Is there, when I look at astrophysics, for example, like the black hole information paradox, the potential solution that has been put forward looks a lot like quantum error correction. And there's elements of quantum information science that are sort of pervading into other subdomains of physics. Is there a sense in which quantum information is changing the way that quantum chemistry
So I would say,
is being looked at?
The further you go, like you go into chemistry, biology, and so on, like obviously the imprint is fainter and fainter. But I think within quantum chemistry, quantum information has had a substantial impact, because I think it's similar to in condensed matter physics. The way we thought about many body quantum states, or things with lots of degrees of freedom, people thought about it. We had theories and formalisms and so on, but it was not as precise as in quantum information. People define resources and they quantify entanglement in the very sort of precise measures and theorems about everything. Whereas the traditional, if you go back and read either quantum chemistry papers or let's say condensed matter physics, someone like Phil Anderson, writing papers in the 60s. I mean, it's almost like reading a story, of what the behavior of everything is, right, with some equations, rather than the very precise way in which things are today. So I think it's had both a conceptual and impact, and of course on the numerical technique side, the computational side, it's also had an important impact as well. So for sure, yes, for sure. I mean, quantum information, broadly speaking, is, I think, had a major impact outside of its application in quantum computing.
Yeah, interesting. So this is really fascinating. Do you have a sense of, is there another sort of sacred cow quantum computing that, like FeMo-co, you're going to tackle next, or is there more work to do with FeMo-co?
I don't view my job as really primarily to have this specific dialogue with quantum computing. It's sort of just a side product along the way. I am actually interested in the reaction mechanism of nitrogenase and solving this problem of the timescale going from 10 to the minus 15 to 1 second. And that's an effort that, one way you can bridge timescales is by building effective theories, not the original physical theories, but physical theories of coarse-grained effective variables. And that's what machine learning allows you to do. So you can essentially, without imagine, learning an effective theory of longer timescales from, just sampling short timescale dynamics, and so on and so forth. So at least in this nitrogenase problem, we are definitely working hard to actually understand the full mechanism computationally, which is a long journey. I mean, it's going to take at least a decade, I think. But I think it will be an interesting one, an interesting journey to travel.
It certainly has been so far. Well, thank you so much, Garnet. This has been really, really interesting. I have found your research over the years to be really fascinating, and I think it continues to be so. So thank you very much for the blog post. Thank you for the paper. Thank you for the continued
thanks for having
work,
me.
and thanks for your time today. That's our conversation with Garnet Chan, and I want to thank him again for the time and the clarity of thinking he brought to what is a genuinely complicated and contested set of questions. The moment that's going to stay with me is his observation that you and I right now are, to a good approximation, not entangled. It's such a simple a statement, and it does so much work. It's the intuition behind why classical simulation handles so much of chemistry so well, and it's the honest foundation from which any serious discussion of quantum advantage in this space has to begin. If you want to go deeper on this, I'd point you to two things in particular. First, Garnet's blog post on the Quantum Frontier site, linked in the show notes at newquantumera.com, is the most accessible companion to the January 2026 paper and addresses the misunderstandings that circulated when the result came out. And of course, the paper itself is also linked from the show notes, and the framing of what was and wasn't solved is very carefully done. Speaking of going deeper, if you want richer coverage of the quantum computing landscape, research developments, conversations like this one, sign up for the newsletter at newquantumera.com. It's the best way to stay connected between episodes. And if this conversation was useful to you, if it sharpened your thinking on quantum advantage claims or gave you better language for explaining explaining the classical quantum boundary to someone else, please share it. That's the best way to support the show, is putting it in front of one person who actually would find it valuable. Subscribe on Apple Podcasts, Spotify, YouTube, or Amazon Music so you don't miss out on what's coming next. Thank you for listening. I'm Sebastian Hassinger, and this has been The New Quantum Era, theme music by OCH. See you next time.